All right, the next topic that we're going to go ahead and look at is solving linear equations in one variable. A little bit of this video is going to be review, but we're going to look at some of the harder topics or harder examples. And some of this is going to be should be new in terms of the material presented at Doñana Community College. If you want to go back and review easier examples, I recommend looking at the videos that are posted for CCDM 114 and Math 1215. All right, let's go ahead and get started with what we want to talk about now. All right, let's just talk about some terminology and also notation. The first thing that we want to talk about is, okay, what is a linear inequality? Linear inequality is a mathematical statement where the equal sign is replaced with an inequality sign. And so we have technically 5 inequality symbols. The first four are the ones that we're most familiar with. It's the less than or greater than symbol. These are known as our strict inequalities because it means strictly greater than or strictly less than. The number on the other side of the inequality is not included. The other two that we have, these are not strict inequalities. They have the bar underneath them. And what they mean is or equal to. So less than or equal to. The other one is greater than or equal to. And the last one that we have is the not equal to symbol. We don't see this one a lot, but except for when we talk about, for instance, solving rational equations, and we talk about the domain of rational equations, we will see the not equal to symbol. And this is technically an inequality sign because, well, it's not an equal sign. All right, so we want to talk about, okay, how are we going to write our answers? Because our answers are not going to be x equals 5, x equals 7. It's going to be a range of values. And so we have 2 basic notations that we want to look at. All right, the first notation that we're going to talk about is set builder notation. Again, we talked a little bit about this in previous videos, but the set builder notation, remember, this is the one that's going to have the squiggly brackets. In order to write it in set builder notation, we want to put the variable followed by a vertical bar, and then we're going to include our inequality statement. So for example, if our inequality is x is greater than 4, the answer in set builder notation is we have our squiggly brackets, we have our variable, which is x in this case, our vertical bar, and then our inequality statement. The way that this is read x. The vertical bar is the mathematical notation for such that, and then whatever our statement is. So for instance, this particular notation is x such that x is greater than 4. Depending on how high you go in math, you may play around with set builder notation quite a bit. The second notation that we have, and the one that we really use the most, is going to be our interval notation. So our interval notation, in order to write this out, we're just going to want 2 things. We want our leftmost value and our rightmost value, and we're going to separate it with a comma. We want to encase these in parentheses and or brackets, depending on if the number or the value is included or not. If the graph goes on forever, we use the infinity symbol. And so remember that if we're on the left side or if we're on the negative side of our number line, we have negative infinity. And if it's going forever to the right, or if we're on the positive side, we use positive infinity. Remember that we cannot equal infinity, so infinity will always use a parenthesis, whether it's positive or negative. If our number is not included, for instance up here, our x greater than 4 is not included in this statement, we would use a parenthesis. And if it is included, if it's an or equal to statement, then we will use square brackets. All right, now let's talk about solving inequalities. So in the previous video, we talked about solving equations in one variable, and we basically do the same thing with our inequalities. We're going to use the same process. We distribute to clear parentheses, we clear the fractions, we combine like terms, we move all variables to one side, all constants to the other, and we divide by the coefficient. We're going to do something a little bit different in here. We're going to introduce something called a compound inequality, or sometimes called a three-part inequality. And so we'll see an example of this in a few minutes, but just remember that with linear equations, remember we had the rule of whatever you do to one side, you do to the other. And so when we talk about three-part inequalities or compound inequalities, we're going to extend the concept. Whatever we do to one part, whether it be the left, middle, or right, we do to all of them. And we're mostly going to be doing things to the middle to get our variable by itself. And so whatever we do to the middle, we want to do to the left and the right side. The main thing to keep in mind when solving inequalities is we do have one little catch, or one little thing that we do need to remember. Remember that if we multiply or divide by a negative, we do need to flip the inequality sign. All right, so now let's go ahead and look at some examples. We're going to solve some inequalities, and then we're also going to talk about writing the solutions in set builder and interval notation, and we'll do a quick review of how to graph these on the number line. All right, let's start with example A. Example A, we have 2x minus 3 is less than x plus 2 over negative 3. Now, when we looked at solving equations that contained fractions, remember that what we could do is we can either write everything with the same denominator. And actually, for this one, what we can do is to get rid of divide by negative 3, on the right side, we can go ahead and multiply by negative 3 to both sides. So if we go ahead and multiply by negative 3 on the right side, again, we're going to do the same thing on the left side. And what we get is negative 6x plus 9. On the right side, our negative 3's just cancel, and we are left with x plus 2. Now remember that we do have a rule that if we multiply or divide both sides by a negative number, we need to flip our inequality sign. So our less than is going to turn into a greater than symbol. From here, we want to go ahead and get all of our variables on one side and constants on the other. Again, remember, it doesn't matter which side you move them to. Me personally, when I'm working with inequalities, I like to always have my variables on the left So I'm going to subtract the x. And since I'm moving my variables to the left, I want to move my constants to the right. And so when we do this, we get negative 7x. My 9's cancel on the left. My x's cancel on the right. And then we get 2 minus 9 is negative 7. We did not multiply or divide by a negative, so we are going to leave our inequality as it is. From there, we want to divide by the coefficient, so we're going to divide by negative 7. We get x on the left side, we get 1 on the right side. And here, because we did divide by a negative, we do need to flip our inequality sign. And so our answer is x is less than 1. Now, just to show you that it doesn't matter, if we go back to the statement up here after we multiplied by the negative 3, you can move your variables to the right, and if we move our variables to the right, we need to move our constants to the left. We still get our 6x's cancel, we get our 2's cancel, and what we have here is 7 is greater than 7x. Here, we can divide by positive 7, and we still get our 1, we still get our x, and because we did not divide by a negative, my inequality sign is going to stay the same. But when we look at our inequality signs, notice that our crocodile mouth is always opening towards the 1. All right, if we go ahead and graph this, we have our number of 1, and we want to shade the direction of the numbers that are less than 1. And that is always going to be to the left. And this is going to be true for either statement. The number is less than 1, or here 1 is greater than the numbers, which is the same sentence. And so this is always going to be going to the left. Now, I mentioned that when I solve inequalities, I always like my variable on the left side. And the reason is because if we put our variable on the left side, the arrow points the direction. Instead of thinking of this as an inequality, think of it as an arrowhead. And my arrowhead is pointing to the left. That is not true if you have your variable on the right side. This one you have to think through a little bit more. The other thing we need with our graph is we need to shade, and we also need to indicate what happens at 1. Is it included or not? Now, you can go the old school notation, and the old school notation uses either closed circles or open circles. We'll be playing around with those a little bit later this semester. And we can put an open circle to indicate that 1 is not included, and we shade to the left. The other notation, which is good for interval notation, is we use brackets. And so here, because it is not included, we use a parenthesis at 1. All right, so if we have our set builder notation, remember that all we have to do is we need to go our squiggly bracket We put our variable, which is x. We put our vertical bar, and then we can put either one of the statements that we have up here. X is less than 1. For our interval notation, we want to know how far to the left does this go. Since this goes forever in the left, at some point we are going to pass 0, and we are on the negative side. And so this goes forever to negative infinity. Our rightmost value of our shading is the 1, and it is going to be a parenthesis because that is what we had on our graph, and it's also not included. All right, let's look at one more basic one. So let's look at example B. We have 1 minus x over 4 is less than 2x minus 2 over 3. We do have fractions on this one, so the first thing that we want to do is we want to get rid of the fractions. We have our least common denominator is 12. And so you can either write both of these with a denominator of 12, or we can multiply both sides by 12. And if we multiply both sides by 12, on the left side, my 12 and my 4 cancel, leaving me with a 3. And so we're going to bring down 3 times 1 minus x. And on the right side, if we cancel, we get 12 and 3 cancel, leaving me with 4. And so we are left with 4 times 2x minus 2. Here we multiplied by a positive number, not a negative, which means that we do not have to flip our inequality sign. All right, from here we're going to go ahead and finish solving. So we can go ahead and distribute to clear our parentheses. We get 3 minus 3x is less than, on the right, if we distribute, we get 8x minus 8. We can go ahead and, on this one, I'm going to go ahead and go positive. So I'm going to add 3x to both sides. And since I'm moving my variables to the right, I want to move my constants to the left. And so what we end up with is 3 plus 8 is 11. My 3x's cancel. I am not multiplying or dividing by a negative, so I'm going to leave my inequality sign the same. We get 8x plus 3x is 11x, and my 8's cancel. We can then go ahead and divide by 11 to both sides. And we get 1 is less than x. Now, if you want to switch this around so that your variable is on the left, well, we can go ahead and do that. I'm going to move my x on the left, my 1 on the right, and again, I want my crocodile mouth opening towards the same thing, and so we want this to be written as x is greater than 1. All right, if we go ahead and graph this, we have our 1. We have that we want this going towards the right because we want the numbers bigger than 1, or because my arrow is pointing to the right when my variable's on the left. At 1, we want either an open circle, or We want a parenthesis because this is a strict inequality again. In set notation, remember again what we're going to do is we're going to put our squiggly brackets. We have our X, our vertical bar, and then our inequality statement. X is greater than 1. For my interval notation, we have our leftmost value of the shading on our graph is at 1. We have a parenthesis around it on our graph, and so we're going to have the same parenthesis in our interval notation. And then this goes forever to the right, which is positive infinity. All right, the next examples that we're going to look at are examples of things called three-part inequalities. And so basically when we talk about three-part inequalities is we have two statements that we're just going to combine into a single statement. So for instance here, when we look at example C, what we have is -4 is less than or equal to 5x plus 1. And (5x plus 1) is less than 21. And so instead of separating this into two inequality statements, we can write it as a three-part inequality. We're going to go ahead and solve this, and basically it's going to be very similar to how we solve any equation or any inequality. The only difference is instead of the rule of whatever we do to the left, we do to the right, the new rule is going to be whatever we do to the middle, which is where our variable is going to be almost always. And I only say almost always because I haven't seen any examples, but I'm not saying that they're not out there. Whatever we do to the middle, we have to do to everything. So we have to do the left, the right, and the middle. Remember that the goal here, just like it was in all of our previous discussions and in our previous classes, the goal is to get the variable by itself. So, again, remember the goal is to get the variable by itself, and so when we look at this, what we're looking at is we are looking at this middle thing. To get x by itself, the first thing that I need to do is I need to get rid of plus 1. So to get rid of plus 1, we're going to subtract 1 in the middle. And again, whatever we do to the middle, we do everywhere. So I'm going to subtract 1 on the left, I'm going to subtract 1 in the middle, and I'm going to subtract 1 on the right. And what we end up with is -5 is less than or equal to 5x is less than 20. We did not multiply or divide by a negative, and so we don't flip our inequality signs. Okay, the next thing that we need to do in order to get our variable by itself is I want to get rid of multiply by 5. And so to get rid of multiply by 5, we're going to divide by 5. And again, whatever we do to the middle, we do to the left, and we do to the right. We are not dividing by a negative, and so we get -1, we keep our inequality signs, and we get 4. So we get -4 is less than or equal to x is less than 4. All right, now when we graph this, just so you kind of see what this looks like, what we're going to do is we're going to plot these two numbers. So we have -1 and we have 4. And I want to know, where are the numbers that satisfy both of these statements? So the numbers that are greater than -1 is going to be on the right side here. And the numbers that are less than 4, so this is the left side of our statement. The numbers that are less than 4 are the ones that are to the left of 4. And the ones that are covered up by both of these, the numbers that satisfy both of these, are the numbers that are in the middle. And that's what we want. We want the numbers. This is an AND statement, and so it has to satisfy both inequalities. All right, so we have the middle shaded. For our -1, we have an or equal to statement, which means that this is going to be a square bracket or a closed circle. And 4 is a strict inequality, which means that it is going to be a parenthesis or an open circle. All right, for our set builder notation, even though this is a three-part inequality, it's still basically the same thing. We have our squiggly bracket, we have our x, we put our line, and then we just put this inequality statement. We have -1 is less than or equal to x is less than 4, and we close it. For our interval notation, starting on the left, what's the leftmost value of our shading? And the leftmost value is -1. It has a square bracket on our graph, and so it will have a square bracket in our interval notation. And then our rightmost value of the shading is the 4. And so that is going to be the rightmost value in our interval notation. In our graph, it was a parenthesis, and in our interval notation, it will also be a parenthesis. All right, let's look at a couple more examples just to kind of practice this. Let's come over to example D. And so example D, we have 4 is greater than or equal to 3x minus 5 is greater than or equal to -17. All right, so we're going to go ahead and solve this. And so the first thing that we want to do is, remember, we're trying to get x by itself. The first thing that we want to do is we want to add 5 to the middle. We're going to add it to the left, and we're going to add it to the right. We get 9 is greater than or equal to 3x is greater than or equal to -12. Again, to get x by itself, the next thing that we need to get rid of is multiply by 3. And so we're going to divide by 3 in the middle. And we want to do the same thing on the left and the right side. And so we get 3 is greater than or equal to x is greater than or equal to -4. All right, so real fast, in terms of our set builder notation, this answer is fine. Okay, we can say x such that 3 is greater than or equal to x is greater than or equal to -4. Now, when we do our interval notation, we do need to be very careful because remember, interval notation goes from smallest to largest. It goes from left to right. And when we plot these numbers on the number line, What we actually have is, if we have 0 in the middle, 3 is on the right, it is not on the left, and -4 is on the left, it's not on the right. So if we put this in the correct order, if you want, you can always rewrite this from left to right. So we can rearrange this. We can say -4, I want my crocodile mouth opening towards my x, and then I want my crocodile mouth opening towards the 3. This is the notation, or this is the notation that's easiest if we're going to graph it and if we're going to write it in interval notation. Here on my graph, we do still want to shade the middle. And we do want to put square brackets on the -4 and the 3, because both of them are or equal to statements. So even though set builder notation, you can write it the way that we had it originally. You can also write it as -4 is less than or equal to x is less than or equal to 3. But our interval notation, there is only one way to write this. It has to be -4, 3, and then square brackets around both of these. All right, that takes care of example D. Now let's go ahead and look at some more that are a little bit more complicated, and we're going to bring in fractions. All right, 2 more examples, and we're going to go ahead and expand the difficulty level again. All right, so we have example E. 1/2 is less than 1 minus 2t divided by 4 is less than 2. We have some fractions. That's the first thing that we do need to take care of. And so again, the first thing that we're going to do is let's go with our LCD. Our LCD is 4. And again, you can either rewrite everything with the same denominator, or you can multiply the left, the middle, and the right by 4. This one, I'm going to go ahead and write everything with a denominator of 4. So for instance, the first fraction, we want to multiply by 2 on the bottom, and whatever we do on the bottom, we do to the top. The middle already has a denominator of 4, and on the right side, we have a denominator of 1, and so we want to multiply by 4 to the top and bottom. So if we go ahead and write this out, what we have is 2/4 is less than 1 minus 2t over 4 is less than 8/4. Just like with our equations, as soon as our denominators are all the same, we can go ahead and cancel them all out. And so what we are left with is 2 is less than 1 minus 2t is less than 8. All right, so now we're back to what we saw when we looked at example C. So again, remember our goal is to solve for the variable. The first thing we need to do in order to get t by itself is I want to get rid of the 1. And so I'm going to subtract 1 from the middle, and I'm going to do it on the left, and I'm going to do it on the right, and we get 1. We have -2t in the middle, and we have 7. We did not multiply or divide by negatives, and so we can go ahead and leave our inequality symbols the same as they were. The last thing that we want to do in order to get t by itself is I need to divide by -2 in the middle, and again, we're going to do the same thing on the left and the right. And so what we have here is -1/2. In the middle, we have t, and on the right, we have -7/2. Now here, because we did divide by a negative, we need to flip our inequalities. So on the left side, I divided by a negative. I need to flip that inequality. And similarly, on the right side, I divided by a negative. I need to flip that inequality. When we graph this, okay, we have 0. We have -1/2 is closer to 0 than -7/2. And so, just like we saw in example B, we can go ahead and rewrite this from left to right. And from left to right, this should be -7/2 t, and then -1/2. And again, we do want our crocodile mouths opening towards the same things. Between -7/2 and t, my crocodile mouth was opening towards my t. And between my t and my -1/2, my crocodile mouth was opening towards -1/2. And so now it's in the same order as what it appears like on the graph. And so we are going to, again, shade the middle. And my -7/2 is going to be an open circle. My -1/2 is going to be an open circle. Or we can use parentheses around both of these. And when we write our set builder notation, we do need to be a little bit careful on this one. The letter that we use in our set builder notation is not always going to be an x. What is our variable for this particular inequality? It is t, and so that is what we want to use in our set builder notation. So we're going to have our squiggly brackets, we have t, we have our vertical bar, and then we have our inequality statement. And again, it doesn't matter what order you write this in. You can still do -1/2 is greater than t is greater than -7/2, or you can write this -7/2 is less than t is less than -1/2. Our interval notation. On the left side of our graph, the smallest number that we have is -7/2. The largest number that we have is -1/2. And again, we're going to put parentheses around both of these because both of them are strict inequalities. Okay, last example, we have example F. We have -3/4 is less than 2 minus t over 5 is less than 3/4. And so same thing, we do have fractions again, so we're going to start with LCD. And so my LCD is going to be 20. The first fraction, I want to multiply by 5 to get a denominator of 20, and we're going to do the same thing on the top. So we get -15 over 20. In the middle, I need to multiply by 4 to the bottom, and we're going to multiply the entire top by 4 as well. And so we get 4 times 2 minus t over 20. And then lastly, on the right, to get from 4 to 20, we want to multiply by 5. We're going to do the same thing on the top. And so we get that this is less than 15 over 20. We did not multiply anything by a negative, and so we don't have to flip any of our inequalities. All right, and then the next step we have is we can cancel our denominators. And we are left with negative 15 is less than. I'm going to go ahead and distribute to get rid of my parentheses. We have 8 minus 4t is less than 15. All right, to finish solving this, we're going to go ahead and subtract 8 from the middle. We want to do the same thing to all three parts. We get negative 23. We are not multiplying or dividing by a negative, so we keep our inequality signs. We get negative 4t. And then finally, we want to divide by negative 4. On the left, don't get so freaked out that we've got fractions. We can cancel our negatives, and we're just left with 23 over 4. In the middle, we have t, and on the right side, again, don't freak out. This is just negative 7 over 4. We did divide by a negative, which means we do want to flip our inequality symbols. And again, if you want, you can rewrite this from left to right. Negative 7 over 4 is less than t is less than 23 over 4. All right, if we graph this, we have negative 7 over 4. We have 23 over 4. We're going to shade the middle. We want parentheses or open circles on both of these, and that's our graph. If we want set builder notation, again, we're going to go squiggly bracket. Our variable is t, and then we write our inequality. We have negative 7 over 4 is less than t is less than 23 over 4. And then if we want interval notation, we have our leftmost value is negative 7 over 4 with a parenthesis, and 23 over 4 on the right, also with a parenthesis. Now, one of the things about three-part inequalities is these are always going to shade the middle. Remember that a three-part inequality basically represents an and statement. And so the only region that can satisfy both is going to be the middle. In the next section, so there are examples where we shade the outside branches, but the outsides cannot be written as a single statement. It is going to be an or statement. And so we will see that in when we get into the next section, A5, and we talk about absolute value inequalities. Okay, for now, three-part inequalities, again, will always be the middle section. All right, that takes care of solving inequalities algebraically. We do have a little bit more for this section, which we're going to talk about next. And we're going to talk about visually how can we apply graphs of equations in order to solve inequalities.